Imagine you are trapped in a massive, complex maze. Your only goal is to find the correct exit hidden somewhere in the winding corridors. If you ask a standard computer to solve this, it tackles the problem by running down one path, hitting a dead end, backing up, and trying another route. It checks every possible path sequentially until it finds the exit. A quantum computer uses a qubit. This tool changes the rules. Through superposition, the qubit behaves like water, flowing down every single corridor and checking every possible path at the exact same time. Through entanglement, every drop is instantly connected. If one stream hits a dead end, all streams know immediately. Through interference, dead ends cancel out, leaving only the successful path glowing brilliantly. A quantum computer calculates by viewing the entire board at once, rather than making individual moves. Building a machine that can hold information in this fluid quantum state is incredibly difficult. These states are highly fragile. The slightest bump, a stray magnetic field, or a tiny shift in room temperature causes that delicate wave to collapse into a regular dead-end bit. To protect that state, engineers build superconducting processors. These machines look like golden chandeliers, and they have to be kept in specialized refrigerators that cool the chips to near absolute zero, a temperature colder than deep space, just to keep environmental noise away. Other designs use trapped ions. This method uses highly precise lasers to grab individual electrically charged atoms and suspend them perfectly still in a vacuum. Because individual qubits are prone to making errors, scientists use error correction. They group hundreds of these fragile physical qubits together to form a single, highly stable unit known as a logical qubit. If one stumbles, the rest catch the mistake. Stabilizing systems through error correction is the bridge moving quantum computing out of theoretical physics labs and into machines that can solve real-world problems. The physical molecules inside our bodies are their own kind of impossibly complex mazes. If you want to simulate how a new medicine interacts with a cell, you have to track the behavior of every single electron in that system. A standard computer gets overwhelmed trying to calculate all those interactions one by one. The system eventually stalls. In the early 1980s, the physicist Richard Feynman realized the solution. He pointed out that nature itself operates on the strange, fluid rules of quantum mechanics. To simulate nature, we need a computer that follows those same quantum rules. Because quantum computers operate using the same physics as the molecules themselves, they act as the ultimate translator. They mimic the molecular system directly, rather than clumsily crunching numbers about it. This gives us a new approach to drug discovery. Historically, creating a medicine has meant physically mixing chemicals in a lab, testing them, watching them fail, and trying again. It is a slow, expensive process of physical trial and error. Quantum simulation allows researchers to build a digital model of a target protein and a synthetic drug, then watch how they snap together entirely on a screen. We are currently in an era called quantum utility, where these machines are just starting to prove useful for scientific exploration. By the year 2035, the industry expects to reach quantum advantage, where quantum computers officially surpass the best standard supercomputers. This shift matters because as a molecule gets larger, its complexity grows exponentially. Adding just one more atom can double the number of variables to track. A classical computer quickly runs out of memory, stalling on problems that would take 1,000,000 years to solve by brute force. But a quantum computer could navigate those same variables in a few days. We have to ask what happens when this maze-solving ability is turned against our digital security. Right now, your personal data is protected by encryption. This encryption scrambles your data into a mathematical maze, specifically designed to take a standard computer thousands of years to solve, one path at a time. In 1994, a mathematician named Peter Shor created an algorithm showing how a quantum computer could use superposition and interference to find the exit to that encryption maze almost instantly. It bypasses the entire puzzle. The hardware is not powerful enough to run this attack yet, but the threat is present today. Bad actors are currently harvesting and storing encrypted data, waiting for the day they can use a mature quantum computer to decrypt it. This is why organizations in finance and healthcare need to prioritize quantum security audits right now. The defense must be built before the attack arrives. The solution is post-quantum cryptography. This is a generation of digital locks, engineered with math that is specifically immune to quantum attacks. Quantum computing shifts the way we solve nature's most complex puzzles, from treating disease to designing a cleaner world. Securing our digital data today ensures we can safely reach that future.